Okay, in this video I'm going to talk about the cyclic quadrilateral formed by the bisectors of the angles of a quadrilateral, like of an arbitrary quadrilateral. So basically here is the setting that we have. So we have an arbitrary quadrilateral, and we consider the bisectors of all of its angles. So we denote this angle by, let's say, alpha and alpha. So these are two equal angles. So the bisector of this angle is denoted by beta. Gamma. And delta. So the bisectors of all four angles. So these four lines, these four bisectors, they, generally speaking, when they intersect, they form a quadrilateral. So like it could be that some three of them, or like even all of them, in theory could intersect in a single point, but generally speaking, they form a quadrilateral. So, and we consider this quadrilateral something like this. So this internal quadrilateral, and so the theorem basically states that this quadrilateral is cyclic. So if we have so if we denote the original quadrilateral as ABCD, then and denote this internal one as MNPQ, so the theorem says that MNPQ is cyclic quadrilateral. And cyclic, it means that there exists a circle that passes through all four vertices of this quadrilateral. So like another name for this notion is inscribed. So if it's inscribed in a circle, inscribed and cyclic, it's the same thing, synonyms. So so let's prove this theorem. So to prove that quadrilateral is cyclic, like there are several criteria, and one of them is that the sum of the opposite angles of a quadrilateral is 180 degrees. So like if we have like any quadrilateral, if we have this, the sum of the two opposite angles 180 degrees, then it's cyclic. So this is the criterion. So that's what we are going to use, and we are going to calculate the sum of the angles. So NMQ plus NPQ. So here, so if I remove this, so basically I'm going to calculate this angle plus this angle, right? So the first thing to notice is that this angle NMQ is equal to this angle, so BMA. and this, well, it's because they are formed by two intersecting lines. And here this angle NPQ is equal to this angle CPD. So let's write this. So this sum is equal to the angle BMA plus the angle CPD. Okay. Now the angle BMA, so we are calculating it. So BMA, this angle, we are calculating it using the sum of the angles in the triangle ABM, right? So the sum of all three angles is equal to 180 degrees. So this can be calculated as 180 degrees minus alpha minus beta. So this is BMA, and similarly the angle CPD is equal to, like, using the triangle CPD, so is equal to 180 degrees minus gamma minus delta, right? So now we can rewrite this as 360 degrees minus alpha plus beta plus gamma plus delta, right? So now what is this alpha plus beta plus gamma plus delta? So this sum is actually equal to so let's write this. So this sum is actually equal to half of all angles in the original quadrilateral, right? Because alpha is half of the angle A in the original quadrilateral, beta is half of the angle B in the original quadrilateral, and so on. Gamma is half of angle C, and so on. So we have 360 minus 1/2 of angle A plus angle B plus angle C plus angle D. And these are angles, the angles in the original quadrilateral ABCD, right? So but the sum of all angles, all four angles in any quadrilateral is equal to 360 degrees. This is true for any quadrilateral. So therefore we can calculate this as 360 minus 1/2 of 360, because this sum is equal to 360. So, and this is equal to 180, of course. So so basically, look where we started. We started with the sum of two opposite angles in the quadrilateral MNPQ that we need to prove that it is cyclic, and we proved that it is equal to 180 degrees, which is exactly the criterion that the quadrilateral is cyclic. So from this we immediately conclude that MNPQ is cyclic, and this concludes the proof of the theorem.